same signal. And what you should get out is exactly the same output as you had the previous day. And that scenario I just described means that I delayed the input to the next day, and what happened, I got out that day the same thing as what I got the previous day, but delayed, occurring the day that I do the measurement. So systems that do not change their behavior with time are called time-invariant systems. That does not mean that signals can't vary with time. That's certainly not the case, but it does mean the system doesn't change its behavior with time. It stays the same. So let's go through a little set of examples and see if we can figure out how to classify signals according to whether they're linear or time invariant. So here we have the gain box. Multiply a signal via an amplifier. Let's say G is bigger than 1 and positive. It's an amplifier. Is that linear? Well, if I change x to x1 plus x2, do I get G times x1 plus G times x2? I certainly do. It's linear. Is it time invariant? Well, I think it's pretty obvious that it is. If I just change t to t minus tau, what I get is the previous expression for y if I stick in t minus tau there. So this is linear and time invariant. No problem with that. Okay, another example. How about the derivative box? Something that takes a derivative. Is that linear? If you take the derivative of a sum, is that the sum of the derivatives? And I think you'll agree. Yeah, sure, that's true. So that's linear. How about time invariant? What's the derivative of x of t minus tau? Well, that's in calculus you learn that's the derivative of x evaluated at t minus tau. Well, that makes it time invariant. So that's we've got two special cases here of linear and time invariant systems. How about this system? How about the squaring system? So the output equals to the input squared. Well, that is certainly not linear, right? Because the square of x1 plus x2 is not equal to x1 squared plus x2 squared. So that is definitely not linear. How about time invariant? If I replace t by t minus tau, is that the same formula I get if I replace t minus tau in this relationship, input-output relationship? The answer is certainly is. So this is an example of a nonlinear but time-invariant system. And finally, how about this system, which is called a modulator? So what we have is our input is here. And what happens is that the system multiplies it by cosine 2 pi fct to produce an output. Well, is it linear? So if I have x1 plus x2, do I get out cosine x1 plus cosine x2? And I certainly do. So that's linear. How about time invariant? So the thing to notice is that the delay applies only to x. So if I replace x here by t minus tau, you don't replace it over here because that's inside the system. That's not the input being delayed. Well, that's not the same expression that you get if you replace t minus tau over here in this formula. You'd have to replace the t in both places by t minus tau. So this system is not time invariant. You delay the input, you do not get the output you had before delayed because this cosine is changing behavior with time. So we have the cases where go through these examples. You can have systems also that are not linear and not time invariant, of course. And the ones that are really going to be special, the ones that are linear and time invariant. We're going to have to deal with this one, but we clearly can't use the linear time invariant system theory to talk about it because it is not time invariant. We'll see that in a second. Well, okay. we now know a lot about systems. What systems do is they operate on input to produce an output for some reason. You might want to amplify it. You might want to delay the signal, take its derivative, whatever. That's what systems do. They can do all kinds of things to signals that are interesting, and by building up structures of simple systems, you can make something that's a lot more complicated than any of the components. And that's basically the way electrical engineers do a lot of design. Break down a complicated input-output relationship into a simpler set that I can realize by cascade and parallel and feedback structures if I can. And I keep emphasizing that linear time invariant systems are very important, what we're going to call LTI. LTI systems really are important. They occur a lot, and as we see when we start talking about circuits, we're going to talk about linear time invariant circuits. When we get to signal processing, I'll talk about linear time invariant signal processing. Those special systems are very important because you can do a lot of very interesting things and have a very good theory for them when we start talking about them. That comes very soon.